Now, there's a concept called freewheeling, and freewheeling is really the same thing as coasting. So that if I have this rear wheel here and my right hand is where the gears would be, as I turn this, I can propel the bike, but then when I stop pedaling the gears, the wheel just continues to spin like this without where my hand is, without the gears turning. So this is a freewheeling system, and it's achieved by two different mechanisms. The difference between the two systems is really where the ratcheting mechanism is located, which allows the wheel to spin freely. In this case here, in this cassette hub, the ratcheting mechanism is in the free hub body of the hub itself. And when I put my cassette on the free hub body of the cassette wheel, then I have a complete wheel, so I can pedal, 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 and I can coast when the wheel is in this situation here. So the ratcheting mechanism is spinning backwards and allowing the wheel to spin freely. In this type of wheel here, a freewheel wheel with a freewheel type hub, there is no ratcheting mechanism in the wheel. The ratcheting mechanism instead is in the freewheel itself, which has the gears, and the gears attach by screwing onto the freewheel. So here's our drive direction, and this is our freewheel spinning direction here. Let me show you. After I put my freewheel on, we see that the two wheels look pretty much the same. I can turn the wheel like this, and now I can coast like this. But in this case, the ratcheting mechanism is in a different place. So both wheels achieve the same end by a different type of mechanism. They appear to be more or less equivalent, but they're really not in terms of their structure. I will put this to motion in a minute, but what you'll see is that as I turn clockwise the free hub body, which is my right hand, that the hub shell will also turn in the same direction, because the pawls here in the free hub body will engage these teeth in the ratchet ring. Here we are pedaling, and the free hub body and the wheel are turning together. When we stop pedaling and start to coast, the pawls are pushed down and out of the way by the rotating ratchet ring in the wheel. So here we are coasting. It's only some very weak springs that allow these pawls to pop up in the first place, and they're very easily pushed down by the rotating ratchet ring. Let's look at these hubs again, the freewheel hub at the top and the cassette hub at the bottom, and see what they look like as structural components of a wheel. I build two otherwise identical wheels, and they look like this. We're going to consider them as installed on a bicycle's rear triangle, like you can see in the photo on the left. Let's put some tires on these wheels and put them into the rear triangle of a bike. I'm riding along on the ground and I hit a bump, and the bump creates a large instantaneous force pushing upward. If we look at the wheel on the left, we have a bearing here and we have a bearing here. They're pretty widely spaced to support that load. On the other side, however, with the freewheel hub, we have a bearing here, and on the right side, the bearing is moved inward quite a bit. So now we have a problem, because we have a large turning moment being put on the axle at that point. Now, freewheel hubs like the one on the right have been around a long time, and they're an excellent mechanism, but they do have one drawback, and that is that the axle is predisposed to bending or breaking because of those loads. I'm often asked this question: are ceramic bearings better than non-ceramic bearings? Specifically, will it make me faster on my bike? And unquestionably, they're more expensive, but if they were demonstrably better in terms of efficiency, it might be worth the money. If you go into any bike shop and you see wheels mounted like this for display, you will see that they always settle so that the valve hole is at the top and the seam is at the bottom. This is a wheel I've built. This has a Alchemy Orc hub in it, one of my favorite hubs, a Pacenti SL23 rim, and Supreme CX-Ray spokes, and Supreme brass nipples. Now, we're going to do an experiment to see how long this wheel spins if I give it a spin and just let it oscillate back and forth. We want to get a sense of how much friction there is in the bearings that will resist that continuous spinning motion of the wheel. Now, the mass of the rim is evenly distributed around its circumference with one exception. Right here, there is a hole for the valve stem of the tube, and opposite that, there is a seam in the rim, which connects the two ends of the hoop together. There is a tiny bit more mass down here where the seam is, and a tiny bit less mass up here where the valve hole is, and we want to see what kind of a difference that makes. I'm going to start the wheel with the seam up at the top and the valve hole at the bottom, and we're going to time this so that we can get a sense of how fast it's slowing down as a function of time. So here we go. Go. We see the wheel start to accelerate slightly, and now it will begin a series of oscillations. And this is after 1 minute. Here we are at 2 minutes. Still oscillating at 3 minutes. At 4 minutes, we still have a small amount of oscillation. And we finally come to a complete stop at 4 minutes and 15 seconds. Okay, let's do one more thing. We obviously know that we have some type of a turning moment of this wheel, because where I have my finger here is the valve hole, over here is where the seam is, so there is a slight turning moment in the wheel caused by that differential of the location of the mass. If I take my finger off here, obviously the wheel is going to start to accelerate. We already know that. But if I put this little baggie on here, which has some nipples in it, and the mass of that baggie is 7 grams, that is enough to stop the wheel from oscillating. You see, it's actually probably a hair too heavy, so something a tiny bit less than 7 grams would cause the wheel to stabilize and not rotate. So from that, I can calculate some facts about how much force and torque and power is necessary to turn the wheel. By the way, it's obvious that this Alchemy hub has some very high quality bearings in it, but the balls inside these bearings are chromium steel balls. They are not ceramic balls, but they are chromium steel balls of very high degree of sphericity. Let's do a little torque calculation. There's the wheel. There's the valve hole. Opposite the valve hole is the seam. That's the radius. And there is a small weight due to the mass differential of one side of the wheel to the other, and that weight is causing the wheel to want to turn. Let's put in some numbers. Our radius is half of the bead seat diameter, so it's 0.311 meters. The mass is 0.007 kilograms. The weight is the product of the mass times the gravitational constant, which is that expression, and I multiply that out, I get 0.069 newtons is the weight. Now my torque is equal to radius times weight, which gives me this expression, and when I multiply that out, I get 0.021 newton meters, or 0.015 foot-pounds. My wheel starts out stationary here, and I have a 311 millimeter radius, 7 grams of mass, and as the wheel starts to turn, it turns through 90 degrees, and the weight has fallen 0.311 meters, and so some amount of potential energy has been converted into kinetic energy of rotation. But my wheel continues to rotate so that 7 grams is now up in this position here, and when that happens, some amount of kinetic energy is converted back into potential energy, and let's say it takes 0.5 seconds for the wheel to rotate that 90 degrees. The small amount of energy that gets converted back and forth is going to be equal to the mass times the force of gravity times the distance that the weight either drops or rises, and that is equal to 0.023 joules. For purpose of discussion, let's assume that I have no momentum going into the position shown on the right, so I have to put in a certain amount of power in 0.5 seconds to raise that 7 grams up to the 270 degree position. And I know that a watt is a joule per second, so my power is going to be equal to 0.023 joules divided by 0.5 seconds, and that comes out to 0.046 watts. That's a pretty small number. Now, hub bearings are incredibly efficient and really amazing structures. It remains an open question to quantify the actual performance differences between them. In any comparison of steel ball bearings with ceramic ball bearings, we have to make sure that we do a so-called apples-to-apples comparison, because ball bearings can vary in roundness, as we've seen, and the ball bearings that are appropriate for a bicycle may not be the same as the accuracy we would demand in the ball bearings of something like a Mars lander. So we have to make sure that we're not comparing rounder ceramic ball bearings with less round steel ball bearings and trying to draw some conclusion. Here are some of the assertions that I hear often. One is that steel ball bearings experience thermal expansion, and that leads to higher friction. If you think about the low operating temperature of bicycles never getting much higher than the ambient air temperature, it's hard to imagine that there's a lot of thermal expansion like there would be in some type of a very high-speed system. And the other is that steel ball bearings compress and become less round, and that also leads to higher friction. If you compare the mass of the rider of the bike, it seems hard to believe that you would actually get any significant compression of the bearing, leading to a change in its spherical nature. Now, just because I articulated those opinions doesn't make it so. What I think we need is a scientifically valid, neutral, blind study of bearings and a comparison of them, and some unambiguous data that is statistically significant. And that data would show us quantifiable benefits, if they exist, that would justify the higher cost of ceramic bearings. If such a study has been undertaken and statistically significant results provided, I have not seen it. Comparing these two might be a pretty good place to start, because I would have chromium steel bearings and silicon nitride ceramic bearings of exactly the same grade. So I would have the same accuracy of sphericity of the balls. That would appear to be a pretty good place to start a comparison. But until I see that, here's what I think. I think that ceramic bearings possibly are better, but probably not worth the expense, because steel ball bearings have a very, very small resistance in the first place. So at best, I think we're seeing a very small improvement to a very small problem. So that was hubs and hub bearings. As I said, there's quite a lot to learn here, and we've really only scratched the surface. You can get as deeply into this topic as you want to.